Hey guys, welcome back to AP Chemistry. So today we are talking about Unit 2. This is going to be about chemical structure and bonding. So in Unit 1, we talked about chemical bonds, how they happen. Today we're going to talk about how those bonds influence the structure of our compounds. Okay. So our vocabulary today, we're going to talk about delocalized electrons, alloys, those have to do with metals, Morse potential curves, sigma bonds, pi bonds, so two different types of bonds there, polarity, formal charge, resonance, hybridization, and isomers. Okay, so a lot of vocabulary here, a lot of new words that you might not have heard before, like formal charge, hybridization, isomer. Those are things that you probably haven't heard about before. Okay, so starting off with metals, right? We've talked about alloys before. You probably heard this word, right? Metallic bonds occur between metals. So in this image here on the bottom, those green circles are our metals. And remember that our metals, on the left side of the periodic table, there are cations. They're positively charged, right? The electrons, because there's no anions here, there's no negatively charged atoms, the electrons are delocalized. What that means is they move freely between all the atoms. So you can kind of see it in the left picture, but it's easier to see on the right picture. The electrons, the red dots, they're moving between the atoms. They're going between all of them. And they're going to keep moving around, right? They're not going to stay still. They move around. And that's how electricity moves through metals. So it's delocalized electrons. We also call it a sea of electrons because they're moving around. They're not staying in one place. Okay. So because of these delocalized electrons, the metals are conductive. So electrons can pass through the metals. They're malleable. Malleable means that they are flexible. They can be flattened into a sheet. So right here we have gold foil. Aluminum foil is also the same thing, right? It could be flattened into a sheet. And ductile. Ductile means you can pull it into a wire. So like copper wire, those different wires, they're ductile. So what an alloy is, it's two or more different types of metals bonded together. So in the image on the left, we just have these red circles, right? These red circles, they're all the same type of metal. That's a pure metal. And then these two, the center and the right, those are going to be our alloys. Because you can see there's more than one type of metal in there. So our substitutional alloy, the one in the center, it's what it sounds like. We're substituting. It's substitutional. So we're taking out some of those red circles and replacing them with blue ones. So we're putting a different metal in there. It doesn't have to be quite the same size, but it's almost the same size. And it just fits right in to the lattice. Our other type is interstitial alloys. Interstitial, right? Inter kind of means between. These interstitial alloys have a second type of metal that's between the other atoms. So we're not replacing them. Now we're just going in between them. Okay, so in interstitial alloys, that second metal has to be a lot smaller. It cannot be the same size. Okay, so let's look at this question here. If we have copper atoms and zinc atoms have the same atomic radius of 135 picometers, PM. Based on this information, which of the following diagrams best represents an alloy containing only copper and zinc atoms? Right, so what we know is we have copper, we have zinc, and both of these have a radius of 135 picometers. They're the same size, right? So if they're the same size, remember we want it to be a substitutional alloy. They're replacing each other. So this first one here, on A, the second metal, it's a lot smaller, so it fits in between. Remember, if it fits in between, that's interstitial. That's an interstitial alloy. On B, we are replacing some of them. They look about the same size, so that is substitutional. That will be our answer, but let's look at C and D as well. For answer C, we have positives and we have negatives. Notice how big these negatives are. So this isn't a metal, actually. This is an ionic compound, right? So this would be something like sodium with bromine or iodine, something bigger, okay? So remember, when we're drawing these, we don't know, if we're drawing an alloy, we don't draw the electrons in there. There shouldn't be any negatives, only positives, okay? And then for D, we only have gray circles. This is a pure metal. We don't have two or more types, so this is not an alloy. So our answer here is B. They're the same size. It is substitutional. Right there, replacing each other. Okay, so for ionic compounds, ionic bonds, that takes place between a metal and nonmetal, right? Remember, that's our positive and our negative, forming a cation, that's the positive, and an anion is a negative. If those are hard to remember, cation and anion, a way to remember it is cation. There's two things in here. First, that T looks like a positive sign. Secondly, we have cat ions are positive. Okay, so whichever one helps you remember, if it's a pun or if it's a T in the cation, cations are positive, anions are negative. Okay, but with ionic compounds, we typically form ionic crystal lattices. So these are 3D arrangements that minimizes the repulsive forces between the atoms, right? So it's not just going to be sodium, chlorine, sodium, chloride, sodium, chloride. They're not going to line up because the positives are going to repel. The negatives are going to repel each other, but we do want the positive and the negative to attract, right? So they're going to do what's in this image on the right here. This lattice structure, you'll see it alternates. We have a negative, then it goes to a positive, then it goes to a negative, okay? The second row, the negative is next to a positive, and the positive is next to a negative, right? So it alternates the positive and the negatives to minimize the repulsion and maximize the attraction. Okay, so ionic compounds do make these ionic crystal lattices. All right, and then this slide here summarizes our types of bonding. So we have metallic, ionic, and covalent. Talking about on this table here, metals, nonmetals, and metalloids. And we have the properties of each one, okay? Make sure you know these properties. Some questions on the AP test can be very simple. You could just ask about these properties. It's an easy question, but we need to know the difference between these. Okay, so Morse potential curves is for covalent bonding. Okay, so we only do this for covalent bonding. And remember, in covalent bonds, the atoms are sharing the electrons. So the electrons are between them to make that bond, right? So for example, H2, hydrogen gas, we have a bond there to connect them. It's being shared. And since we're sharing electrons, the nuclei have to approach each other, right? We have this hydrogen, we have this hydrogen. There has to be some overlap. So if we draw it like a Bohr model, or H is just one, this other H has to overlap it. So these nuclei are approaching each other. Remember, nuclei are positive. They're going to kind of repel each other. Okay. So what the Morse potential curve looks at is we're looking at the distance between the nuclei and the energy of the repulsion. Okay. So we're seeing an internuclear separation, which is the distance between the nuclei and the bonded molecule. And that tells us the strength of it, right? So the closer together we are, the stronger the bond. The further apart, the weaker the bond. Okay, so let's take a closer look at this graph here. So this is what a Morse potential curve is going to look like. On the y-axis, we have energy, so the energy of the bond. The x-axis is the internuclear distance. So that's the distance from the center of the nucleus to the center of the other one. Okay, the center of the two nuclei is the internuclear distance. So you'll see in this one, we are from 0 to 74 on the x-axis. So we're getting we're getting bigger as we go to the right. So to the right is bigger distance for the bond. And then for the y-axis, this one's a little weird. We're not starting at 0 down here. Our 0 is up here, kind of in the middle of the graph. So as we go up, that is more energy. As we go down, it is less energy. Okay? So be careful when you're reading these graphs. You will have negative energies down here. Okay? But if we look at the curve, the red curve here, we start off high. It goes down to form this like a inverse peak. And then it will go back up and plateau out. Notice how this plateauing here, it stays below 0. It's approaching 0, but remember in algebra it's an asymptote. It's never going to touch the 0 line. Okay, so what this is showing is farther to the right, these nuclei are so far apart that there's no energy between them. Okay. As we start to get closer, so as they're moving closer, there's some energy of repulsion, but we can still move closer. It's not quite there yet. Okay. As we get to this peak down here, at that point, that's when we have the optimum distance, right? So that's where we want to be to have the bond formed. If we keep going to the left, if we go up this, that means we're getting so close together that the nuclei are pushing away from each other so much, and it's just going to make it go back down. Okay, so this point here is the important one. That is the optimum distance for the lowest energy of the system. That's where we want to be. Okay, so for hydrogen gas, for H2, we want to have a distance of 74 picometers, and the energy would be whatever number would be right there. Okay, so that's how you read a Morse potential curve. Okay, so the Morse potential curve shows the energy and the distance. Okay, that lowest point there is the optimal distance for bonding. And when we say optimal distance for bonding, that means attractive and repulsive forces are balanced. That's why they can hold onto each other and stay there. Okay. So let's look at this question here. All right, so we have a Morse potential curve for H2. This was the graph that we were just looking at. Okay. It's asking how would a Morse diagram for Cl2 compare in terms of bond length and bond energy. So we need to sketch a graph of Cl2 on this graph here. Okay. So first, let's talk about our compounds. We have H2. I'm going to do H2 in blue because that's what's on the graph. And I'll do Cl2 in red. Okay, so let's compare the two of these. So if we're just looking at the atoms, for hydrogen and Cl, the radius, so the size of them, chlorine's a bigger atom, right? So if chlorine's a bigger atom and needs more space before that overlap, so the distance between the nuclei are going to be, it's going to be bigger, right? Versus the H2, if they're smaller, that distance is smaller. Okay, so if the distance is bigger, we know that we're going to be further to the right because our distance is bigger, right? Remember, the x-axis is our radius, our distance. And then for energy, if we have a bigger bond, it's going to have less energy. Less energy does not mean more negative. It means closer to 0. So our energy is going to be a little bit closer to 0. Okay. So what our graph's going to look like, we're going to still have that same downward start. Our peak is going to be further to the right and further up. And it's going to come back up and plateau by 0. Something like that. Okay. These drawings don't have to be perfect as long as you show it to the right and slightly up. That's what we're looking for. Okay? The only time it would have to align with numbers is if they give you numbers. So if they told us like 150 and negative 300, that point, that peak should be down there. So it'd be something like that. Okay, but if they don't give us numbers, as long as it shows directions to the right and up, we're good. Okay. So this Morse potential curve is asking us to label the curves for these three compounds. We have CO, we have N2, and then we have O2. Okay. So right off the bat there, we can separate one of them, right? We have triple bond in CO, triple bond in N2, and a double bond in O2. Those two lines, a double bond, since there's less bonding, it's going to be weaker there. Remember, weaker bonding should be further out, less energy. So we know our yellow curve here is going to be our O2. Let me write that, it's kind of hard to see. Our yellow is going to be O2. Okay, so now we're between CO and N2. Okay, these both have triple bonds. They're both pretty close on the periodic table, so we can't really do it based on size or strength of the bond. This is going to be based on something we're going to talk about here in a minute called polarity. You've talked about polarity before. Remember, polarity is when it's uneven. So here, CO, our oxygen is a little more electronegative, so it's going to be pulling more of the electrons to it. For N2, they're equal. So there's an equal share, there's no dipole moment, right? So for CO, because it is polar, it's going to be a little bit stronger. So our CO is going to be our stronger bond, and our N2 is going to be slightly weaker, but it's still a good bond, strong bond. It has a triple bond there. Okay, so that's how we're going to compare the potential curves. We're going to compare them based on size and distance, like we do for H2 and Cl2. We're also going to compare them based on strength of the bonds. Okay? All right, so moving on, we're going to talk about some covalent bonding. Right, so we know that there's single bonds, double bonds, triple bonds. This is how many electrons are shared. So a single bond is one pair of electron. Remember, a pair is 2 electrons. Double bond is 2 pairs of electrons. Triple bond is 3 pairs. You can see images for those down here. So H2 is a single bond, O2 is a double bond, and an N2 is a triple bond. Okay, so we have 2 questions here. The first one is, what is the relationship between bond length and strength, right? So as it gets stronger, right, a stronger bond is going to pull on itself more. If it's pulling more, it's going to be closer together. So the stronger bond, so if we increase strength, it's going to be closer together. So we're going to decrease distance, right? So that's why our triple bond has the highest energy, the highest strength, but the shortest bond length. Okay, so our triple bond is going to have the highest energy, but the length is going to be the opposite. I'll put a D for distance. Okay, so single bond is going to be the biggest with the weakest energy. Triple bond is the smallest with the most energy. Okay, the second question here asks us to compare these compounds from the highest to lowest energy in terms of bond energy. Okay, so let's first draw these compounds out so we can see what we're working with. We have HCl, HBr, HF, and HI. Okay, so these are all single bond compounds. They're all covalent compounds. Okay, so remember, let's look at some intermolecular forces. For HCl, HBr, HF, and HI, they're all 2 different atoms. So they all have London dispersion forces because it's covalent. We have a small amount of dipole, right? And then remember, for hydrogen bonding, for hydrogen bonding, that's hydrogen connected to either fluorine, oxygen, or nitrogen. We have that here. So HF has hydrogen bonding, so that's going to make it the strongest. So starting with this is the highest to lowest. So HF comes first. That's going to be our highest energy. Okay. Then between the other three, we're going based on distance of the bond. Okay, so on a periodic table, group 17 are halogens. We have fluorine, chlorine, bromine, iodine. Okay, so going down that list, iodine is going to be the biggest, fluorine is going to be the smallest. So the bigger the bond, so HI, is going to be weaker because further apart. The closer together it is, so HF is going to be stronger because they're smaller atoms that can get close together. So we're just going to go based on size. So after HF, we have HCl, then we have HBr, then HI is going to be our smallest. Smallest energy, but biggest bond. Okay, so when you're ranking bonds, start with looking at intermolecular forces and the forces between the atoms, then go based on size. Okay, also with covalent bonding, we can describe them based on the orbitals, right? So when bonds happen, we're overlapping our orbitals. So we have two different types of overlaps. We have a sigma bond, and this Greek letter, that's like O with a curvy top, that's the lowercase sigma. Okay, sigma is an overlap between the s orbitals. Okay, so an s orbital is going to be the first bond the first orbital that overlaps to form a bond. So every bond is going to start with a sigma bond. After that, the p orbitals are going to overlap to form either double or triple bonds, and those are going to be our pi bonds. Okay, so that Greek symbol you probably recognize, that's our pi, right? We use that in math as well. So pi bonds form the double or triple bonds, and this is overlapping of p orbitals. Okay, so if we're looking at compounds, right, our first bond is going to be our sigma bond. So our first line is our sigma. Then each line after that is one pi bond. So O2 we have one pi, N2 we actually have two pi bonds. Okay, but always start with the one sigma. Each additional one is a pi bond. So what I want you to do here is look at this molecule, and you're going to count how many sigma and pi bonds we have here. Okay, I want you to do this on your own first. So if you need to pause it, you can. Then check back here. Okay, but remember our sigma bonds are single bonds. So each single bonds and the first bond of double or triple. So each first bond, I'm going to color in blue. And then we're going to count them. Okay, so for sigma, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sigma bonds. And then for pi bond, it's each additional bond in double or triple bonds. So in the CC double bond, we have 1. The CC triple bond, we have 2. So 1, 2, 3 pi bonds. Okay, so that's how you count sigma and pi bonds. Okay. Then moving on to polarity. We've talked about this a little bit with dipole moments, right? But polarity is based on the difference in electronegativity. So on this slide, I put this here as a reference, this periodic table with the electronegativity values. If you were in on-ramps, you had to remember the numbers for this second row, 1, 1.5, all the way to 4, right? It changes by 0.5 each. You don't have to memorize the numbers for AP. If you need them, they will be given to you, okay? But what we're looking at is a difference in the electronegativity. And remember, electronegativity is higher in the top right with fluorine, and it's lower in the bottom left. But we have two different types of polarities. We have nonpolar and we have polar. Non-polar is more balanced. So more balanced charge has an electronegativity difference of 0.4 or less. So if we look at this here, right, let me erase this arrow. If we have, say, a carbon-phosphorus bond, right? So if we have a carbon-phosphorus bond, carbon is 2.5, phosphorus is 2.2. The difference in that, 2.5 minus 2.2, is 0.3. That's less than 0.4. So that would be non-polar bond. A polar bond is not evenly shared, so it has a bigger difference. So it has a difference of 0.4 to 1.7. And when we have this not even share, if it's not balanced, we call that a dipole moment. Okay, so an example of that, like with hydrogen bonding, no, not with hydrogen bonding. Yeah, it was hydrogen bonding, sorry. So N with H, I'm right up here so I have more room. Nitrogen has an electronegativity of 3.0, hydrogen is 2.1. If we subtract them, our difference is going to be 0.9. That falls between the 0.4 to 1.7, so that is going to be a polar bond. Okay. So in polar molecules, we can indicate the distribution by assigning partial charges. So these are not going to be full charges, right? So with ionic compounds, we can have Na plus and Cl minus, right? We have our charges assigned to them. With covalent, if there's a polarity, we can assign partial charges. Partial charges are the symbols right here. So that is our delta. So that Greek letter is delta, and either has a positive or negative. The delta indicates that's the partial, not a full charge. Okay, so if we look at H2O, right, we know oxygen is more electronegative, hydrogen is less electronegative. So the more electronegative is going to pull the electrons closer to it. So our electrons are going to be a lot closer to oxygen than they are from hydrogen. That makes our hydrogens a little bit more positive. They're partially positive, whereas our oxygen is partially negative. Okay, that's what the partial charge means. So we can see that here also. These bubbles show the electron density. So the smaller the bubble, the less electron density there is. So we can see by the fluorine, there's more electron density, so it's going to be more negative. Okay, so the region that the electrons are going to is going to be slightly more negative. Okay, so let's look at these questions here. The first question is, using polarity, think about why ionic compounds are typically soluble in water. Okay, so with this one, remember when we talk about polarity, you probably heard the term like dissolves like. Okay, what this means is like polarity dissolves like polarity. So if compounds have similar intermolecular forces, they have similar polarities, they're going to dissolve each other. So water, we have that here. It has some partial positives and negatives. It has a dipole moment, right? It has the hydrogen bonding, so it has a distribution of the electrons. Ionic compounds like NaCl have charges, right? And so since they both have either partial charges or full charges, they can dissolve in each other. And since they're both polar, right, the polar compound, it can dissolve in each other. And when it does dissolve, it does what this image shows here. The negative side of our oxygens, so remember the reds are oxygens, are going to surround the positive cations, the sodium, and then the positive sides, the partial positives of our hydrogens, are going to surround our negative from the chlorine or chloride. Okay. So anytime we have polar compounds, this is kind of what it's going to look like when it's dissolving. It's going to surround it based on polarity and partial charges. Okay. The second question says the elements carbon and selenium have the same electronegativity value of 2.55. Which of the following claims about the compound that form C and Se are more likely to be true? So we're looking at a carbon-selenium bond. And the difference in the electronegativity, that's weird, difference in the electronegativity is it's going to be 0 because they're both 2.55. So 2.55 minus 2.55 gives us 0. Okay, so if it's balanced, if it has a difference in electronegativity 0, it is going to be stable. It's going to be a balanced bond. So it's going to be nonpolar, right? So A says it's unstable. If it's bonded together, it's going to be stable. Okay, unstable things are not going to bond. B says it's going to be nonpolar covalent. That sounds right. It is nonpolar because it has less than 0.4 electronegativity. And there's two nonmetals, it's covalent. C says the compound has the empirical formula of CSE. I mean, it might, but we don't have any information about masses, so we can't validate that. And then D says a molecule of the compound will have partial negative charge on the carbon atom. Well, if we have electronegativity difference of 0, that means our electrons are going to be smack dab in the middle. They're not going to be to one or the other, so there's no partial charges. So that's not right. So our answer there is B. Okay, so let's look at these. So we have, the first question here is identify the following as polar or nonpolar. So for identifying polarity, we want to draw the Lewis dot structures first. So CO has a triple bond, N2 has a triple bond, NH3, we have nitrogen in the center, 3 hydrogens, and a lone pair on the nitrogen. CH4 has 4 hydrogens on the carbon, and then H2O has oxygen in the center with 2 pairs of electrons. Okay, so for polarity, we want it to be uneven. So for CO, the carbon-oxygen triple bond, this is an uneven bond, right? But carbon and oxygen are really close to each other on the periodic table. So this is actually going to be nonpolar. For N2, I put an oxygen there instead of nitrogen, sorry. For N2, these are 2 of the same atom, so the difference in electronegativity is 0. That's going to be nonpolar. For NH3, we have a lone pair of electrons here. So that's going to pull the negatives to the top. So the lone pair is going to be partially negative. The hydrogens are all going to be partially positive. Okay. So this is going to be polar because it's uneven. Carbon is an even distribution all the way across. It's symmetrical. This is be nonpolar. And then for H2O, this looks symmetrical. But remember, this is just our 2D drawing. With VSEPR, if it has 2 lone pairs and 2 bonded groups, it's actually a tetrahedral geometry. That means we have our atom in the center of that oxygen. We have our 2 hydrogens coming out in the corners. And then it's kind of hard to draw here, but we have one of the lone pairs. I'm going to draw this as a dashed line going to the back. And then one of the lone pairs, I'm going to draw this solid line coming to the front. So the one going to the back is like going into the screen. The one coming to the front is coming out of the screen at you. So really it's like an X, but kind of inverted. It's like if you stand with your legs apart, one hand in front of you up and one hand behind you to up as well. Okay, that's what it kind of looked like. We'll see. We can look at this with molecular models in class as well if that's kind of hard to visualize for you. But so here we have the electrons on the top. That's going to be more negative on top. So this is going to be a polar compound. Okay. So be careful with your drawings. Make sure you know VSEPR because that's going to help you determine polarity. Okay, I want you all to do this second question on your own. I'll give you the answer here, but I want you to look at this, and you're going to be ordering or ranking the bonds from least polar to most polar. Okay, so look at the distance from the atoms on the periodic table. And you should get HF is the most, OH is second, NH is third, IF is fourth, and OF is fifth. Okay, but I want you to make sure you look through each of those compounds and rank those polarities. Okay, and the last question down here is explain the following based on VSEPR. So this kind of question is something that would show up on an AP test, right? You're talking about polarities, but you're also talking about VSEPR. So the first one is PF5 is nonpolar, but IF5 is polar. So let's draw these out. PF5 looks something like this. IF5 looks like that with a lone pair on the iodine. Okay, so that has an expanded octet for both of those. Okay, so to answer the question, PF5 is nonpolar. Using VSEPR, we can say that this is a trigonal bipyramidal geometry, right? And they're even on all sides. So trigonal bipyramidal geometry, remember, has 3 in a line, like a triangle, and it has 1 that comes up and 1 that goes down. Okay, so that makes it nonpolar. For IF5, our VSEPR geometry here is going to be trigonal pyramidal. No. Hold on. Square planar. Or sorry, square pyramidal. We have these 5 here, right? That's going to make kind of like a square shape that's flat. That fluorine on the bottom is going to come down. And the lone pair of electrons is going to be a force on top that pushes them down. Right, so you're going to have this square shape with this one on the bottom that makes a pyramid. So that's square pyramidal. And if it's square pyramidal, that means that we have something on one of the sides that is a lone pair of electrons, right? It's not shown in the molecular geometry, but it's shown in the electron geometry. So based on that VSEPR arrangement, we know that it is going to be polar. Okay, so make sure if it says using VSEPR as your answer, you say the geometry, right? We said the geometries. And then we mentioned that PF5 does not have a lone pair, but IF5 does have the lone pair, making it unbalanced. Okay, I want you to do the same thing with CO2 and CO3 2 minus. Okay, so CO2 looks like that. And CO3 2 minus looks like this. Okay, so each of those 2 oxygens on the right have a negative charge. Okay, so I want you to think about the geometries here and explain why they are both nonpolar. Okay, so going on to formal charge. Formal charge is looking at the actual charge of the atoms. These are not partial charges. So we can see here, like with CO3 2 minus, that has a -2 charge. That is an actual charge, it's not just a partial charge. We don't write the partial charges into the compound formulas. Okay, so there is an equation to calculate the formal charge. So you can read through these if you want, but the simple one is going to be this one down here. This is one I use. So the formal charge is going to be the group number, so it's number of valence electrons of the atom. So this comes from the periodic table, minus the number of covalent bonds, so it's how many atoms it's attached to, minus the number of electrons in lone pairs. Okay, so let's look at an example with this. So it says draw the correct Lewis dot structure for NO3 minus, right? So if you have nitrogen with 3 oxygens right, we need, so if we count valence electrons, nitrogen is 5, each oxygen is 6, so 6, 12, 18. And then we have a minus there, so we have one more. So 18 plus 5 plus 1 is 24. We need 24 electrons in our drawing. So we have 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's 24 electrons. Okay, but our nitrogen isn't full. So what I'm going to do here is I'm going to take one of these lone pairs and I'm going to make it into a double bond. Okay, so we can have that. We can also have other variations of this, right? We can make double bonds on all of those. We can leave that double bond as a lone pair, but let's look at it with the double bond here. Okay, so we have our nitrogen, we have our single bonded oxygens, we have 2 of those, and then we have our double bonded oxygen. We only have 1 of those. Okay, let's do the formal charge equation for each of these. So for nitrogen, our group number on the periodic table is going to be 5. That's how many valence electrons it has. The number of covalent bonds, right, on this nitrogen, we have 1, 2, 3, 4 bonds. So it's going to be minus 4. And the number of lone pair of electrons, we don't have anything on the nitrogen, so it's going to be 0 there. So nitrogen has a formal charge of positive 1 there. Okay, let's look at the single bonded oxygens. So for the single bonded oxygen, the group number is 6. Okay, for the single bonded oxygen, number of covalent bonds, we only have 1 there, so minus 1. And the number of electrons and lone pairs. Okay, so this is going to be our individual electrons. We have 1, 2, 3, 4, 5, 6. So minus 6 gives us a minus 1 charged overall. For the double bond oxygen, we have 6 valence electrons. We have 2 bonds there, so minus 2. And then we have 1, 2, 3, 4 electrons. So 6 minus 2 minus 4 is a charge of 0. All right, so we have a plus 1 for the nitrogen. Remember, we have 2 of these single bond oxygens, so overall that's a minus 2. And then a 0 for the double bond oxygen. So for a whole compound, we have a minus 1 charge there. That matches, right, because we had NO3 minus. That matches our charge for the compound. So this is going to be the correct drawing based on formal charge. Okay, so be careful with formal charge. They might ask a question about this where you have to calculate it. This equation is not on your formula sheet. You need to make sure you know how to do this. Okay, moving on to resonance. So if we have a formal charge on a compound and we have some double bonds, we can have what's called resonance. And this is when electrons move around in order to balance the compound. Okay, so if we look at this image here, if we have that HCO double bond O on top with the minus on the single bond oxygen, these electrons are just going to move around. So remember what this really looks like is, let me erase this. This hydrogen has 2 electrons to the carbon, which is 2 electrons to this oxygen. And then the oxygen on top has 4 electrons. So what can happen is this lone pair of electrons can move down to the carbon to make a double bond. And if it does that, the carbon is going to be a little overwhelmed, right? It has more than the octet, more than the 4 bonds. So what it's going to do is it's going to take the 2 electrons on top here and throw them onto the oxygen, because the oxygen can handle it, right? So when that does that, that's going to be those 2 electrons on the top, making it negatively charged. But now our oxygen on the bottom has a double bond, and that's going to be neutral. It's going to have a charge of 0. Okay, so our electrons can move around a little bit. This can be tricky to get used to for drawing them. What I would suggest is looking at some examples and trying to work through some practices. You'll have some practices for this in your practice packet. But if we look at this one here, we have SO3 2 minus. Okay, one way to draw this is we have, so we're going to have the 3 oxygens. And when we draw resonance, we want to have the lone pairs all drawn in. Okay, so on our oxygens, we're going to have something like this, and we want one double bond so that sulfur can have 4 bonds on it. Okay, if there's no double bond, if an oxygen has 1 bond and 6 electrons, that's going to be negatively charged. So that's our 2- charge there. Okay, this can change if our double bond here, if these electrons move down and kicks its double bond up, right? So we'll still have the sulfur in the middle with 3 oxygens, but now our double bond is going to be on the oxygen to the right. Sorry, I drew an extra pair of electrons here. Okay, so now we have still 2 negatives, but they moved around. Okay, and then we can have a third resonance structure if these electrons move down and kick the negative up. And that will be the sulfur in the middle, the 3 oxygens still. But now the oxygen on top has a double bond. Okay, and then these 2 oxygens on the bottom have the negative charges. So throughout these structures, we have the -2 charge regardless. It's just the position of the electrons changed. So the way we're going to draw this, you don't have to draw the arrows if you don't want to, but you do need to have those negative charges, the ones that I drew in red there. You need to have them on the atoms. And then we're going to encapsulate all this in brackets and put a -2 charge on top, because SO3 has a -2 charge. That's the way you're going to draw a resonance structure. Okay, so hopefully that made sense. If it doesn't, I would suggest coming in for tutoring, asking about it, looking at other examples. The more you look at this, the more it'll make sense. All right. And then moving on to our last 2 topics. First, we have hybridization. So we said that sigma and pi bonds are from overlapping orbitals, right? So that's what we call a hybridization. If our orbitals overlap, it'll hybridize to make a kind of a different looking orbital there, but it's still sharing electrons. Okay, so with our hybridization, it depends on the amount of electron regions we have. If we have 1 region, it's just an S hybridization. If we have 2 regions, sp1. If it's 3 regions, it's sp2. So we're just stacking up each time. 4 regions is sp3. And remember, p only goes to the 3. So if we have additional regions, they're going to go to the d. So sp3d1 if we have 5 regions. Okay. So what this looks like is if we have this compound down here, let's determine the hybridization of each numbered atom. Remember, we're only looking at shared electrons. So we're only looking at, we're looking at electron densities. So we're looking at, for this oxygen, we have 1, 2, 3 electron densities. So S comes first, we have 1 of those. Then each additional 1 goes into the P. Okay. Don't write it like sp1, p2. Combine like terms. So S and then p1, p2 going to combine for p2. Okay. For our second one down here, the carbon, remember electron densities. We have 1 with the triple bond, 1 with the single bond. So S is going to be our first one. Then we have 1 in the P. So sp1, if you want to write that 1, you can, but you don't have to. Okay. Our third one down here, this one's a little harder because it's not drawn out. But remember, this looks like the nitrogen connected to the oxygen, the lone pairs, and then we have 2 hydrogens. So it's 1, 2, 3, 4 electron-rich regions. So 4 is S is 1, and then we need 3 in the P, so sp3. Okay. And our last one is this carbon up here. We have 1, 2, 3 electron-rich regions, so 1 in the S, 2 in the P. Okay. Be careful with this when there's double bonds or triple bonds. That's still 1 region of electron density, even though there's more than 1 pair of electrons there. All right. And then our last topics are isomers and functionality. So when we talk about isomers, isomers are molecules with the same molecular formula, but they're arranged differently. So these are some examples of isomers. We're only going to look at this blue area here. We're only going to look at the constitutional isomers for AP chemistry. Okay. The other ones, if you take organic chemistry in college, you'll learn about all of those as well. But for constitutional isomers, you can see that they have the same molecular formula, right? These are both C3H6, 7, 1, 2, 3, 4, 5, 6, 7, F. Okay, they're both the same thing, C3H7, F. The difference is where the fluorine is. On the top one, the fluorine's on that center carbon. The bottom one, the fluorine's on the right carbon. So even though they have the same formula, the bonding is different. The atoms are arranged differently. So that makes it an isomer, a constitutional isomer. Okay, so that's all you need to know about isomers. It's the same formula, but arranged differently. And then I added this onto here. This is not something you necessarily need to memorize for AP chemistry, but these are definitely good to know. It'll help you out. If you take organic chemistry again, you will need to know all of these. But these are ways we label compounds in chemistry, right? So you've probably heard of like alcohols. So things like methanol, anything that ends in -ol is an alcohol, right? So anything that ends in -ol. So methanol, propanol, any of those. We have alkanes for single bonds, alkenes for double bonds, alkynes for triple bonds, right? So these are a lot of things that you see in chemistry and compounds, and that's good to know the general name of them just to make it easier when you're looking at a compound. This is not something you have to memorize though, again, okay? Okay, so that is it for Unit 2. That is it for structures and bonding. For Unit 3, our next unit, we will move into talking about gases, I believe. Okay, so make sure you watch that video before we start a Unit 3 notes, or a Unit 3 unit, sorry, and take those notes, and I will see you then.